And just so you guys are aware, gonna go ahead and record this one today, especially since I'm not sure if Edwin's gonna make it. He asked that get a copy just in case he didn't make it today and he can check it out later. So Noah, questions before we get going, then we'll just pick up where we left off with our ASHRAE conversation. I did include in your documents a ASHRAE exercise, kind of for some more practice, manually calculating the ASHRAE formula. So that's in the folder marked as exercises. So if you guys want to spend a little more time on the formula, you can work on those exercises with some more examples. Though on the exam, as far as the formula goes, remember how there was the 3 steps. The first step that established the base rate, and then the second one that was the fan deficit, where we went and measured all the exhaust fans. And the third one was the infiltration credit. So the infiltration credit, you're not gonna have to do that during the exam. They might ask some questions sort of related to it, like the leakier your house is, the more credit you're gonna get. But they're more, the formula questions are gonna be not too bad. They're not gonna be too many, but they might ask you certain things like what is our deficit for exhaust fans, and give you a couple fans and whether or not they have windows. And you'll have to calculate that deficit. So just adding up how much the fans move versus how much they should, and figuring out those deficits, and we can get a credit of 20 CFM per operable window. But the real BPI exam is closed book, but you can use that BPI 1200. And if you're having trouble remembering that formula, it'll be right there. And for the ASHRAE 2013. So we were just finishing up with that formula, and now we're going to get to the actual fans themselves, some different options, and then how we are going to duct them out properly, vent them out so they're going to actually move the amount of air that they're rated for. So exhaust fans come in basically 3 different styles. Most common is the exhaust only. We collect the air at the source and blow it out of the building. Just your regular bathroom fan, kitchen fan. Now there is such a thing where they run backwards, can blow air in, but in our climate, not very desirable, especially during the winter, have cold air blowing into the house. Another technique that brings the air in is return on the, or fresh air intake on the return of the furnace. So that's another style that brings air in when the furnace is on. And then the third category is the balance. So it's the same amount of air that's being sucked out of the house is getting blown in. And then we're also capturing the heat with the heat recovery, or the heat and the humidity in an energy recovery ventilator. So some different styles, of course, exhaust only being the most common. So here's just a quick look. 2 bathroom fans, exhaust only, right at the source. So the fan's right at the ceiling, collects the exhaust right out. Most common, and probably what we're going to be doing most of the time. But some situations we might we might still do a regular exhaust only fan, but we might also do some other techniques like supply only, where there's air intake installed on the return. And this can be really useful in trying to correct pressure balancing issues when the furnace is creating too much of a negative pressure in the house and can even backdraft the furnace, the water heater, wood stove, fireplace, whatever they might have. So this would have an effect on the home of pressurizing it. So if anything was backdrafting and those exhaust gases were coming into the house, this would help push them out and help prevent that. Of course, there is going to be energy penalty with that, blowing cold air in. And if we want to use this in our ASHRAE calculation, then we're going to have to measure the flow through that little fresh air intake, which is going to be difficult, as we won't be able to use our exhaust fan flow meter on that. We would have to use a flow hood or pitot tube to measure that flow. But most people aren't trying to meet ASHRAE this way, but it can be useful in solving backdrafting issues. And sometimes we show up and they already have a system like this. The super good sense mobile homes, most of those have some sort of fresh air intake on the return. Sometimes those are installed with a backdraft damper, so that only comes on when the furnace is on, and then when the furnace is off, it shuts the damper, so it's not having that air coming in all the time. And the reason why it's going into the return is so that it can be conditioned, heated, or cooled and not be so uncomfortable. And then HRVs, heat recovery ventilators, these are best suited for homes that are really airtight. They need a lot of fresh air coming in, more so than a regular bathroom fan style would be able to provide. So these can do several hundred CFM, but they are definitely far more expensive, both the unit and then the labor to install it. And these are best suited with their own dedicated set of ductwork. Though we'll look at, I think I have a slide with some photos of one that's connected to a forced air furnace, which can work, but sometimes that might mean running your furnace fan to move the air, which is going to be a lot more expensive to run a furnace fan all year round. But the idea is not only to get the fresh air in, but to capture the heat that would have been wasted while maintaining the pressure in the house. So keeping it neutral where it's not being depressurized or overly pressurized. And the ERV takes that one step further and captures the moisture, the humidity, which is good in dry climates, where we don't want to overly dry the building, and we want to keep some of that humidity so we don't have health problems and cracked skin and bloody noses. Recently, Panasonic's come out with a sort of mini ERV where it exhausts the bad air, brings in the good, but it is an ERV, so it is going to capture some of that humidity, which is desirable in a dry climate like a lot of Eastern Oregon, but maybe not so in more humid places where we're trying to dry the building out more. I asked Panasonic if they were going to make a HRV, and the problem they are running into with a mini HRV is the condensate. Since it does have a drying effect, we gotta get that moisture somewhere safe where it's not gonna rot or grow mold, and they're having big issue with that. So a mini HRV in the bathroom would have to have a condensate line installed and go to a drain, and that's not easily accomplished from up in the attic. But the ERV version doesn't require that, and can be useful depending exactly what our goals are. The main benefit is going to be a balanced exhaust. So it's not going to cause the house to be depressurized when it's on, because it's going to be bringing in the same amount of air that's going out, capturing the heat out of it. And in the ERV, also some of the moisture, the humidity. These units are a little spendy, about $400 or $500. It's a little more than a regular exhaust fan. And then we're going to have to install it. So this is giving us a more detailed look at a HRV or ERV that's been installed with the forced air furnace. So we're capturing or bringing in the fresh air from up on the roof. And it's going through the heat exchanger of our HRV, and the good air is coming through there, picking up the heat and delivering that to our return to be conditioned and distributed through the house. On the other side of the system, we're collecting the bad air at the bathrooms, and then they're running through the heat exchanger and going out the sidewall in this case. And that can be good for trying to bring in a lot of mechanical ventilation, more so than a regular bathroom fan could move. We could move several hundred CFM with the HRV versus the 100 or so with the bathroom fan. Then there's a whole series of smart switches, some of which can be combined with existing fans to make them meet ASHRAE requirements. Though you do want to make sure the fan and the switch are compatible. You know, some fans are DC and some switches are not, and vice versa. So just want to make sure they're matched so that it won't burn the fan out prematurely. But if they have a newer fan, we don't necessarily need to replace a brand new fan to meet ASHRAE. We might be able to just install a smart switch that can give it the features of ASHRAE fan, like running on low speed continuously or running on a schedule to accomplish the same amount of airflow. There's also humidistats, but depending on your climate, they might not be a very good choice. Because if these work by setting it to a humidity level, let's say we want to keep it at 50%, so the fan's going to kick on when we go over 50% humidity. But if it's more than 50% outside, it may not ever shut off. Just going to keep running and running and not be able to get it dry enough. Then sometimes we might run into other situations where we need more air coming in, especially when it comes to combustion appliances. And I think on Monday, we're really going to dive into combustion appliances and how they operate and what kind of things making them backdraft. But exhaust fans play a big role in that. And we might need to take that into account before we close out a project. That way we make sure everything works properly and we don't leave the house in an unsafe situation. Once we've selected our fan, now we got to vent it. And these venting principles apply to all vent types, whether it's our heating ducts, our exhaust fans, our flues, dryer vents. All these principles are applicable to them. And that's going to start with the fact that a hard, smooth duct is going to have less resistance than a flexible, corrugated pipe or duct that has all these speed bumps. So it's going to have more resistance and a lower flow. So hard duct is definitely the preferred method, and depending on the circumstance, usually is mandatory too. We want longer radius turns. We don't want it our airflow restricted by being overly crushed or pinched shut. So we can have good airflow through there. And also as short as possible. This photo is a little small, but you can see that these are heating ducts, but each run is a whole box of flex duct. They didn't cut it to fit. So some are, 10, 20 feet longer than they need to be. So by the time the air moves all the way through and comes out the other end, it's lost a lot of momentum, and it's going to be less air coming out. There's a couple charts that we can use to help us size our exhaust fan ducting properly so we don't run into flow issues. Now, there is fans that will ramp up automatically to overcome resistance in the ducts, but that comes at a price. That's going to use more electricity, so it's going to cost more money than if we had just vented it out better, not causing that restriction in the first place. So even though there are some fans that can ramp up, when they do, it's going to move the same amount of air, but we're going to have to pay that penalty. So it's better just to vent it right in the first place than rely on it to keep ramping up to try and move the desired amount of air. This chart here is right out of ASHRAE, and it's called a prescriptive duct sizing. So this can help us determine how far we can run our ducting for our fan, depending on what kind of fan and what kind of duct material. So it has this part here, 80, 100, 125, that's the fan flow. And then we've got on the left, the flex, on the right, the hard duct. If we went with 4-inch flex on an 80 CFM fan, which in Oregon, that's what we're required by local specialty code at a minimum, we would only be able to run at 3 feet. And that's not going to cut it at, even if we are 3 feet from venting it out, because each elbow is going to add an extra 15 feet. And then the termination is going to add 15 to 30 on its own. So we're going to be way into the negative. We bumped that up to a 5-inch. Now we got 70 feet. So we got enough room for some elbows and a termination and still have a few feet. If we go all the way up to 6-inch, which a lot of these newer fans are made for 6-inch duct, then there's not any limit. Now we don't want to go crazy, but we don't really have to worry about the flow being restricted. So bigger is better up to a point. If we vented it with a 14-inch duct, fan's probably not going to be strong enough to push it all the way out, but there wouldn't be any restriction from the ductwork itself. But I would recommend going 5-6 inch as a default, and that's going to keep you in the clear most of the time. We're not going to have flow restrictions. Now, since we're normally doing hard duct, if we were tempted to just go with the default 4-inch, it sounds pretty good, 35 feet, but we take off an elbow or two. Now we just don't have enough to go anywhere, especially once we have a termination. So this can help us in advance before we do anything. Is our plan good, or are we going to have problems if we try to install it this way? So this is prescriptive duct sizing, which goes well with this chart. Also at ASHRAE, this is the equivalent duct length. So this is how we can, the last chart was our maximum length. This one is going to estimate our equivalent duct length, so we make sure we don't go over the last prescriptive one. So the formula is going to be how many linear feet. So in this case, we got to run a 12 feet, and they want to go with 4-inch flex aluminum duct. So the higher quality duct work that you often see in new construction for venting out the fans, pretty standard. They want to go with that. So that has a multiplier of 1 1/4 because it is flex and it's going to have a lot of resistance. So that's going to take that into account there with that 1 1/4. We estimate 1 elbow, and then we have a termination, and that termination is going to account for equivalent of 30 feet. So we just sum that up, and we get 60 equivalent duct length, even though we're really only running it 12 physical feet, but the equivalent with the elbow and the termination and the flex duct is going to be 60. So then we can use the last chart and make sure we're not going to be over our limit. So if we come over here to our 4-inch flex, 3 feet. So we're way over. We're going to have serious airflow problems. But if we bump that up to 5-inch, we'll be good, and we'll still have even 10 feet left over. So let's look at one more example here. If we have an 80 CFM fan with 2 elbows and 20, we got to run at 20 feet. Can we get away with 4-inch hard duct? So we want to use 4-inch hard duct. That gives us 35 feet. And if we got to run it 20 feet with 2 elbows and a termination, we're going to be way over. So just the elbows alone is going to eat up almost all of our duct length. But if we bump it up to 5-inch, we're going to have plenty to work with. We got enough for termination and go several feet longer than most houses, even plenty of length. So bigger is better, so we have good airflow. The lower our airflow is, the more our ASHRAE fan is going to have to make up for these fans that don't move enough air. And then if our ASHRAE fan isn't moving enough air, now we're not in compliance. So we would fail inspection and we would need more airflow to meet ASHRAE. So we definitely want to get it vented well so we don't run into those sort of issues where the fans aren't moving enough air. Now, normally when we think about ASHRAE, we're thinking all about the exhaust fans, which is the main part of ASHRAE, but it also has some other miscellaneous requirements. We've mentioned all about bathrooms and kitchens need 50 and 100 CFM to meet the requirement for the spot ventilation. But ASHRAE also requires that any penetrations between the garage be sealed, and that's regardless if it's cost effective or not. Any obvious penetrations need to be sealed, including, if necessary, weatherizing the door, weather stripping it, but also any penetrations sealed around any where the wall between the house and the garage, where that's framed, like at the bottom of the wall plate or drywall in the garage might have some gaps that might need to be sealed, as well as any penetrations. And that is to maintain good indoor air quality in the house. We're not going to be able to do that if we have a lot of communication between the house and the garage, bringing those contaminants in. Clothes dryer has to be vented to the outside. That's a requirement. The ducts are going to need to be sealed when they're outside the conditioned space. That's a requirement too. Regardless if it's cost effective, ASHRAE doesn't have that sort of requirement. It just states that this is what you need to do to meet these requirements of ASHRAE 62.2. So you gotta seal the ducts. They do have a standard on how tight they want the ducts, but for exam purposes, we'll just stick to the BPI requirement, which is 10% of the furnace airflow, not the square footage. It has nothing to do with that. It's the furnace airflow, which means now we need to know how much air is going through the furnace. We can measure it in kind of a lot of the same ways we do exhaust fans, like with a flow hood or a flow plate or a pitot tube. Or if nothing else, we can check what the rated flow is at least. New fans that we install have to meet the loudness requirement, the zone requirement. So continuous run fans, that means no more than one zone, while intermittent fans can be up to 3 zones. And those are new fans, not existing. This doesn't apply to existing fans. We're going to have to measure the flow of the new fans. And if that is doing 2 jobs, like ASHRAE plus bathroom fan, so whole house plus spot ventilation, then we'll have to measure the 2 different fan speeds, the low, continuous, and then the full speed. And we want to make sure that our fan gets set to the proper continuous run setting or equivalent intermittent schedule. For example, let's say ASHRAE, we run our formula and it says we need 40 CFM continuous. Well, if we have an 80 CFM fan and we run it half of every hour, or we run it 12 hours on, 12 hours off, that's going to be the equivalent of that 40 continuous. but on an intermittent schedule. And a lot of agencies are opting for this, I think, in hopes that it will help keep the fan from getting so dirty as easily when it's running 24/7. Either way is perfectly acceptable. Just want to make sure you calculate what the intermittent equivalent is, and that can be done easily with the ASHRAE calculators that are available. Don't worry about trying to do that manually. So another thing with ASHRAE 62.2, and when they first rolled this out in 2010, there was a lot of misinterpretation of what this meant. So if we read it carefully, it says that we need a MERV6 filter installed in our furnace, or with our furnace, with our ductwork, when we have a duct that is longer than 10 feet that brings in fresh air from outside. So if we have a fresh air intake on a long duct, that duct is going to need to be filtered with a MERV6 or better. That way we're not bringing in contaminants from the outside, pollen and other things. How this was interpreted back in 2010 was, and this was no one in particular, it was the whole country thought that this meant that every home that we went into that was forced air, we had to put a MERV6 filter in. That was later clarified. No, only if that furnace is bringing in fresh air from the outside. When we install the ASHRAE fan and set it up, we want to make sure that it is labeled, how to turn it on, or what the switch that operates it is for. Since the fan is mostly silent, the homeowner might flip the switch and not realize it does anything and could end up turning it off when it needs to be on. So the switch has to be labeled, or if it runs without a switch, then the fan needs to be labeled on how to turn it off, which could be inside the fan. So you could say controls behind the fan, or if there's not any controls behind the fan, then at the breaker box. Because there's going to be times the homeowner is going to need to turn it off, clean it, service it, or if the outdoor air is really bad. We had the fires in the gorge not too long ago, and the air quality outside was just terrible for quite a while. So that'd be a good time to kick off your ASHRAE fan temporarily because of the fires outside, but normally it's going to be on 24/7. Then we have to provide the homeowner with information on how to maintain it, clean it, and keep it running. So some other resources, there's the ASHRAE standard, though that isn't very user-friendly. Instead, I would recommend the user manual, which is a separate document, and it's got lots of Q&A and photos, and it's written in plain English. That can be really useful. And then the calculators. There's a whole bunch of calculators. In Oregon, they used to allow us to use some different ones, but it sounds like mainly they want us to use the red calculator, which I don't have on this slide, but if you just Google the red calcs or red ASHRAE calculator, it'll come right up. Or you can always send me an email, I'll get you the link. So in this section, we covered a lot of information from what the different contaminants are in the house, how to reduce them or eliminate them, or if we can't, just dilute them down with our fans. We covered what kind of fans are required, like spot fans in the bathrooms and kitchens, and then usually a whole house fan, which can be located in the bathroom or kitchen. And most of these are going to do double duty, so they'll have low whole house fan setting, low speed, and then a full speed for when we need to use the we need to bathe or cook, we can kick it on to high. We covered how to test the exhaust fans and spent a good amount of time going over the calculation itself. And remember, as we air seal the house, make it more airtight, and we put in these exhaust fans, that's going to create a depressurization effect on the house where the pressure is going to get lower and lower. And if we have combustion appliances, sometimes that can interfere with their operation. So we want to be sure and thoroughly test our way out of the project to make sure we are not creating any health and safety issues. We're going to dive into how to perform that test during the combustion safety presentation, but we just want to make sure we're not creating these problems by keeping the rate as low as possible. We don't want to go over the limit or over the minimum requirement. We want to keep it as low as possible so we don't have problems, and we help keep the customers' utility bills down. So if you guys have any questions, be sure and ask those now or drop them in the chat box. And then I'm going to bring up the quiz for this section. All right, so you should be seeing the quiz, plus you got a copy in your documents. 4 questions. Let's give about 10 minutes to give you guys a chance to go through and answer these. If you have trouble with the math, we can go over it together, but just give it your best, and you can use the slides to help work on this. So I'll give you guys some time to work on that, and we'll go over the answers at about 1:55, so 5 till 2. So I'll give you guys till 5 till, and I'll just be on mute so you have some peace and quiet while you work on this. All right, everybody have a chance to make their way through all these questions. Let's go over the answers together. On number one, a home has a bathroom fan with 34 CFM, no window, and a kitchen with no fan, but does have a window. What is the local exhaust adjustment? Anyone want to volunteer an answer?
Hey, Dan. Yeah, so I was gonna say I'm not exactly sure what it is for the required exhaust fan flow for the kitchen. I had answer A for 16 CFM.
All right, it's a good guess. Now, all three of these numbers are steps in the process. And that's how the BPI questions will be, especially when it comes to math. But only one of them is going to be the correct step that they're looking for. In this case, like how Drew answered would be 24 CFM, because the question is basically what is the formula of the second step of ASHRAE for the fan deficit. That's where we go through, and the bathroom fans need to move 50 CFM and the kitchen fan's 100. So if we start with our bathroom fan, we get a deficit of 16. But that's not what it's asking. The question wants us to do this for all the fans. So if we started with the bathroom fan has a deficit of 16, and the kitchen has no fan. So the deficit for the kitchen would be 100, because it needs to move 100 and it's moving 0. But it does have a window, so that brings it down to 80 because of the credit. So if we have 100, but we minus the 20, and see what do we get? Yeah, 96 when we add this all up. But that last step of the formula is going to be divided by 4. So I hope that makes sense, breaking it down step by step.
Yeah, thank you, Dan.
You bet. I'm just glad I could figure out how to write on the thing. And if you want more practice working on these formulas, there's the exercise, and that's in your reference folders. And we're dividing it by 4, and that is a part of the formula. It's always the same. You sum up your deficits, and you're going to divide it by 4. The 4, that number is selected on purpose. It has to do with the exchange rate of air in the house, but we won't spend too much time on that since that's not going to be on the test. So moving on to number 2, which of the following are typical or possible contaminants in a residential home? This one, circle all that apply.
So I'm just gonna give a couple answers, Dan. I think mold it could be common in residential homes depending if they have high moisture. Dust mites, I think that's relative as well. Asbestos, depending on the age of the home. I mean, I guess you can have products, but I'm mostly thinking of vermiculite and popcorn ceiling, so a little bit older homes. So I'm thinking D, B, A. Right there.
That's it. A great explanation. Yeah. A, B, and D. It's not impossible to have arsenic in the house, but it's not very common. Very few products have arsenic that are designed to go inside the house. You know, outside the house, a different question, but inside, not common to have arsenic. And then the ultraviolet rays was kind of just a bogus one. Though that might change now with COVID. A lot of talk about using ultraviolet to sterilize the air, but we won't get into that. So moving on, number 3, what is the first step of reducing a contaminant inside of a residential home?
Answer B.
That's right, you got it. If we can, our first priority is to get rid of it. If we can't, maybe we can encapsulate it and then last dilute it.
Yeah, so I think I had it was B or C. And when I think of encapsulate, I'm thinking of getting out of the living area. So, but yeah, eliminating it would obviously be the best, right? Obviously.
Yeah, that would be the most correct. Encapsulation would be right behind it, though. You know, the next
Okay.
thing. So the last question here, let me see if I've figured, there we go. This one's another math formula, having us run through, get some practice on that. There we go. All right, so we've got a home, 1,900 square foot, 3 bedrooms, 1.5 stories in Portland, blower door, 1650. And it's just going on. It's got all the information for doing really all 3 steps of our ASHRAE. So anyone make it through this question number 4 and come up with the right answer? Or did your answer match one of the options at least?
I came up with answer C, 41.
Man, you got it. That's correct. And on the real exam, this question has you going through all 3 steps. But on the real BPI exam, they're going to be breaking it down. They'll either have you do the first step or the second step. Not usually going to have them both in one question. And they're not going to be testing you on the third step, but it's good to know what goes into that infiltration credit, how it's calculated. They're going to want you to be aware of it, but not necessarily have you do the full formula. But that is great work. Anybody else come to that same answer of 41 CFM? So if we break it down, I don't want to spend too much time on this, but if we break it down, the formula on how to calculate this, we got the base rate, which was 3% of the square footage. So we'll take the 1,900 CFM or square footage, and we're going to multiply that by 0.03. So that's going to give us 57. Then we got 3 bedrooms plus 1 gives us 4, and we're going to multiply that by 7.5, which is going to total to 30, which gives us 87 for the first step. Second step is all about the exhaust fans. We've got a bathroom and a kitchen. Bathroom has an operable window and a fan that moves 35 CFM. So we have a deficit for that of, because it needs to move 50, but it's only moving 15. But then we have a credit of 20. So these kind of cancel each other out. But then our kitchen has no window and a fan that moves 75 CFM. So our deficit's 25, but we have no window. So that will be our total for our fans. So we'll just divide that by 4. And we're going to tack that on. It does give us a quarter. Sometimes BPI will round up or down. The last step is going to be the infiltration credit. So we're going to take our CFM 50 and we got to convert it to a CFM natural. So to do that, we're going to take 0.0, see if I remember what this number is, 52. And multiply that by our blower door. Multiply by our story factor. If we have a 1.5 story, our story factor is going to be, anybody know this off the top of their head?
1.18.
1.18, thank you. And the weather factor, if you don't mind, for Portland.
0.52.
Thank you. 0.52, I'm going to run out of space. And then we're going to multiply that all straight across. 0.052, 1650, 1.18, and 0.52, which is going to give us 52.6, 164, and we're going to subtract that off of here. So we have 87 plus 6.25 minus 52.64. We get 40.6, and we round that up, and we get 41. If you're still having trouble with this formula or any of the steps of it, take a look at that exercise. And if you can complete it manually, go ahead and take the information, plug it into one of the calculators, and then see if you can figure out how to get there to that same result. Check your work. Now the calculator is going to be a hair different depending which one you go with, but it's going to be ballpark within just a couple CFM. So hopefully that helps just summarize that formula one more time. Though if you guys have any other questions, I'm happy to answer those now or later. If you think of something also, that's fine. All right, well, if you guys think anything, let me know. So we'll go ahead and move on to the next presentation, which is going to be, before we get too far ahead of ourselves, let's head back to our base load from the other day and make sure we give that its proper time. And in the base load section is not too lengthy, but there's some things we're going to be covering about just calculating base load and what kind of measures save on the base load, as well as just reviewing what the base load definition is. Just a few key terms, lots and lots of supplemental links and reference information, all in your lesson plan. I'm gonna go ahead and bring the presentation up. And this is number 5, presentation 5. Let's make sure that's up on your screen. So you should be seeing that up on your screen now, baseload measures.
There we go.
Cool, thanks for confirming. Make sure you got it on your screen. All right, baseload measures. In this presentation, we're going to be focusing on how baseload affects the heat load of the home. We're going to go over different things that we can do to reduce baseload, and we'll also go over how to calculate how much of their utility bill is coming from or associated with the baseload usage. And that's going to be evaluated with 5 quiz questions at the end. So let's start with, what is the definition of base load? You know, depending what kind of field you're in, base load can mean a lot of different things. In weatherization and energy home performance, we're talking about the energy, this can be electric or gas or other, that the home uses but is not associated with heating or cooling. So it's kind of the energy they're using all the time except for heating and cooling. So it should be somewhat constant every month, whereas heating especially is going to be almost exclusively during the winter when we're trying to keep the house warm. So it's everything else. Just a quick couple examples of ways to save on measure or things that use a lot of base load. Lighting, getting LED lights in, upgrading the refrigerator to Energy Star, maybe improving or even replacing water heater, and using low flow faucet aerators and water fixtures. So before we even go out to our house, or we can do it at the house too, but we want to be taking a look at their utility bills so we can tailor the audit to their usage to help them save the most. So it's a good idea, even before you do the audit, to get their utility bills, at least a year's worth, and start to figure out, are they a high user or average user? And where is most of that energy being used? Is it seasonal or is it base load? Then we can focus on ways to go after that usage for more savings. Like if their main usage is on base load, putting all of our effort into seasonal is not going to be necessarily the best bang for our buck, not going to do them the most good. Now, when we're looking at utility bills, or we're just calculating how much energy they use, not all units of fuel are going to be in the same unit of measurement. We've got natural gas In our part of the country, in Oregon, that's mainly by the therm. So usage is by the therm, and a therm is 100,000 BTUs. And a BTU, just so you have that fresh, is British thermal unit. And it's the amount of heat it takes to raise 1 pound of water 1 degree Fahrenheit. The key being there, pound, 1 pound of water. We don't normally think of water in pounds, but it's that amount of heat, which is about roughly the amount of heat from a regular wooden kitchen match. So the best way to compare other fuels is to convert them all to BTUs, and then everything can be apples to apples. Some parts of the country, though, use CCF, and I believe that's Roman numerals, but like my water bill is by the CCF, but my gas bill is still by therms. And each different kind of fuel will have a different amount of heat per unit, since they're different types with different units. Just kind of gives you an idea, as well as the price. I think these prices were from 2010-ish. Natural gas is down at super cheap, well below $1. Oil went up, but it's not as high as it's has been in the recent past. Propane just fluctuates a lot, especially with oil prices. Usually cheaper though than oil. Electricity is usually the most expensive way to try to heat a house. Every kilowatt of electricity contains about 3,412 BTUs if you round it. And that's the magic number for converting electricity into BTUs, 3,412. So let's look at a couple bills, put this together in the big picture. Each company is going to be different, but for electricity, we're going to be looking at the kilowatt hours and their usage. And we do want to get the whole year's worth. If we only have a couple months, may not be a good representation of their whole year's worth of usage, especially for missing winter. Anymore, you can get these online and makes it real easy. So the base load is the fastest growing part of anyone's energy usage. Traditionally, space heating was the biggest portion, but as we get more and more devices and gadgets, space heating is making up a smaller and smaller portion, especially as we get more efficient heating systems installed. And it helps just further compound that shrinking of the space heating. Some homes can have more plug load, base load usage than space heating. So this is just kind of giving us an idea of where things fall in the average energy usage. This is from EIA, I think 2008, 2010-ish. So it's space heating shrinking, lighting shrinking, refrigerator shrinking a bit, especially compared to 20, 30 years ago. But the total amount of usage has remained about the same because the plug load has grown so much and it's taken up that sort of slack. It's that sort of take back. So in households that have electric heat, about half of the electricity on average is for the base load. So that can be a lot of their usage. So what we're going to do is, preferably before we do the audit, we're going to get a hold of a year's worth of their utility bills. That way we can calculate their base load from their seasonal to help us focus our audit when we go out to the house. And then when we come back to the office and we put together our building modeling software model of our home, we're going to use that not only to tailor our audit, but to make sure our model is accurate, because we'll have their actual utility bills. And when we create our model of the existing house, we'll be able to customize it until they align. That way we have a good base model to recommend improvements to the home. And we can be as accurate as possible. So to calculate the base load, we're going to take their year's worth of utility bills, and we're going to average the 3 lowest months, the shoulder seasons, when they're not using any or very much heating or cooling. Once we've averaged that, then we'll have the average monthly usage. If we want to know the total years, we'll just multiply that by 12 to get the whole year's worth. While we're out there, if we notice anything unusual on their utility bills, like they had a lot of usage in the summer, and we want to follow up on that, check out and see if they have air conditioning or something else was going on. Do they have a hot tub or a pool, or just family over? Or maybe they had some months where it was the opposite, very little usage. Maybe they went on vacation, or the furnace was broken down. We can ask the homeowner and find out what exactly is going on, try to have a better understanding of their energy usage so we can make the right recommendations. And then we can get that into our building modeling software, see what's going to be cost effective. So let's do a quick example here of their electric base load. So we'll get their year's worth of utility bills. And so now we've got month by month and the total usage. To find the base load, we're just going to take the 3 lowest, the shoulders, season or months. We're going to add those up, divide by 3 to find the average. And that gives us roughly 500 a month. If we add that up, we get 6,000. If we divide that by their total usage, that turns out to be about 31% of their bill. So most of their usage is on the heating, but still a sizable chunk on the base load. So we'd want to focus mainly on the heating, but keep an eye out for any low-hanging fruit on the base load side of things that could help save there. And another reason why it's good to get the whole year's worth of utility bills is that their cycles are not always even. You know, sometimes we've got a range here, 29, 28, 30, 35, 28 days in a cycle. So they don't necessarily match the calendar cycle year, where 1 month can be several days more than that actual month. But if we have the whole year's worth, then we don't have to worry about a long or short cycle. Let's do another example here. We got all their utility bills. We plot that on there month by month. and we get our total, and right away we can see that their total usage is quite a bit less than the last house. It was like 19,000. This one's only 4,000. So right off the bat, we know that they're a much lower user compared to the last one. And that might be they have a small home, or not very many people living in there, or they're just really focused on saving energy. But it also could be that it's an apartment and they're getting a lot of basically free heat from the neighbors. So if we calculate our base load, we're going to take the 3 lowest months, add them up, divide by 3, we get roughly 276 per month. And we figure out how much that is of their total usage is 76%. Most of their bill is going to base load. So when we go out for our audit, we would want to focus in, what is using so much base load? Why is the total usage so low? Is their furnace just doesn't work? They don't heat the house? Or are they heating through another way, like with wood that we wouldn't see on their utility bill? Or gas, oil, propane? Is an apartment that they don't really need to heat because the neighbors keep it hot enough that they get enough heat? And we can help tailor our audit to focus on what's going to save them the most. This chart's just kind of giving us some ballpark range of what kind of energy usage is associated with different appliances. This is just on average. A lot of these appliances have Energy Star versions that use far less energy and more so every day. And just as we tighten up energy usage requirements. Well, it gives you an idea, like fridge can use a lot, clothes dryer, if it's electric, definitely uses a lot. Clothes washer can, or even like plasma TVs use a ton of energy compared to other types of TVs. But just give you kind of an idea where they all fall on the spectrum. So this really generalized rule just kind of giving us an indication when we should be focusing on doing more on saving on base load. So if they're using more than 600 kilowatts per month without an electric water heater, or if they do have electric water heater, if they're using more than 1,000, because water heater is going to use a lot. But also if they're just their percentage of usage is high, then that can be worth going after too. So some things that really affect our base load and how much energy is going to be used are the number of occupants, number of people in the house. The more people, the more energy they're going to be using, and that's going to drive up the base load. And similarly, the equipment in the house, like the fridge and the clothes washer and dryer, those are going to be affected also by the number of occupants, but also by their size. Are they a smaller unit, or is it industrial size clothes dryer? That's going to have a big impact on how much energy is used. And really also the habits of the occupants. Sometimes people do different things that can use a lot of base load. Like I'm sure you've been into homes where the occupant leaves the TV or the radio on in multiple rooms. Sometimes they might have everyone on in the house, and the reasoning might be for their animals. They like to keep They like the sound. They might have some sort of rationale behind it, but it can be a big energy waste. Or if they leave their computer or TV entertainment systems on 24/7 because they don't want to wait for it to restart or anything, that can be a big energy usage. Well, let's start to break down some of the bigger components, things that we can save easily on baseload, starting with our lighting. And lighting has come a long ways in recent, just the last couple decades, at least on the residential side. You know, not too long ago, incandescent light bulbs were basically the only ones you could get for a regular Edison bulb fixture. Then we had the CFLs, and that eventually led us to LEDs. CFLs are still really great in a lot of situations, and they save 75% over a regular incandescent light bulb. And lighting isn't our biggest part of our bill, about 7 to 10% or 11%, somewhere in that range. But if we can reduce that by 75% by swapping out the light bulbs, that's going to be cheap and easy. Let alone if we get LEDs, are going to be at least 90% efficient. So even though only 10% of their bill is going into lighting, if we can knock that 10% down 90%, we just saved a big chunk of their bill pretty easily. When we're picking out replacement light bulbs, it's becoming pretty common knowledge at this point that looking at the watts is not going to work with newer lighting like CFLs or LEDs, where in the past we relied entirely on the watts to know how bright it was. But now with energy efficient ones, that's not a good way to describe how bright it is. So instead we'll use lumens and how much light is actually being produced instead of how much energy is being consumed. And when we replace a bulb, we want to make sure we're replacing it with something equivalent so that the homeowner doesn't end up with a light that can't put out as much as the old one. They're going to hate it. They're going to go back to using their old light bulb. So we've got to match the lumens, if not exceed what it was before, put in a little brighter. Some other things to be cautious of when replacing light bulbs: not all energy efficient ones are going to be compatible with dimmers and photocells or have other specialty features. So if the homeowner really needs those, make sure you're selecting a bulb that is dimmable or can be used on a photocell. And they do make those in, I think, both CFLs and LEDs. LEDs are going to be better as they're more efficient, but there's also the property of the light, the color, the warmth of it. Is it a cool bulb, a warm bulb? And that can be described in two different ways. We have the color rendering index, CRI, which basically compares the quality of the light to the sun, as we hold that as our best light source. So we use that as the scale. Higher the number is better, the more natural it is. But that doesn't have anything to do with the color of the light, which is associated with the temperature of the light, and not in Celsius or Fahrenheit, but in Kelvin, the absolute temperature of it. And that's what's going to depict what if it's going to be a warm or soft or natural or cool bulb. And those are best in different situations depending on the area you're trying to illuminate. Is it a work area? Is it ambient lighting? And so on. Now, with CFLs comes mercury. With incandescent light bulbs, they quite often contain lead. And CFLs are lead free, but they do contain mercury. Mercury is poisonous, but the amount of mercury in a CFL is incredibly minute, far less than a drop. It's a fraction of a drop inside of it. And that's how fluorescent lighting works. It has a phosphorus coating on the bulb. You know, those the long tube style ones, when you break those and it has the powder in there, that's the phosphorus. And when we add the mercury vapor and then the ballast at the end send the right amount of electricity, and when that vaporized mercury is energized, reacts with the phosphorus and it creates the illumination. So definitely is mercury is poisonous in high amounts. The amount in a bulb is not very much. So if one breaks, the glass breaks, well, the mercury is gone at that point. It's evaporated and nothing to worry about unless you're like breaking it in a confined space, like a paper bag or something. That's a different story. But if you drop one, then mercury is gone. So you can just sweep it up, carefully clean it, throw it in just in the garbage. But if the bulb burns out, doesn't break, that mercury is still in there. Not the best thing to be filling the dump full of. So they do recommend that you recycle them, and anyone who sells them is supposed to be able to take them back to recycle them. But all the big box stores do for sure, Home Depot. So we can recycle dead, non-broken ones that way. But the amount of mercury is really pretty small. And when you compare it to the amount of energy saved, even though at first you might argue, okay, well, we're saving energy, but we're adding all this mercury to the environment. Well, let's back up a second. Where does electricity come from? In the US, most of our electricity comes from burning coal. And what is the byproduct of burning coal? It's mercury. And though we've gotten better at having cleaner coal, but it's still not 100%. So when we use CFLs, we're actually putting less mercury into the environment because we don't need as much electricity, 75% less. So those coal plants, we're reducing that need and offsetting our mercury versus the exponentially more that would have been produced from the electricity that was made at the power plant. But this is kind of an issue of the past. Now with LEDs are lead and mercury free, and they last far, far longer. One of their big benefits is that they can last decades compared to incandescent light bulb lasts about a year on average. CFLs more like 10 or 15. LEDs gonna be closer to 20 or more. So it's a quick overview on lighting, which is gonna be on the exam, but not a huge part of it, but a few things when it comes to base load. One of the bigger parts of base load, especially older fridges, can use a ton of energy. This green one here is quite old, probably is using $20 or more a month. And a new one, a new Energy Star fridge uses maybe $4 a month. And the older it is, the more it uses. I've seen fridges that use $40, $50 a month. And that's per fridge. You got 2 or 3 of them. You're just going to multiply that up. So we do want to scope out the fridge for replacement whenever it's going to be cost effective. Now, I know in Oregon, some agencies have refrigerator replacement programs, some don't, especially in the more rural areas, a little harder to get contractors. But for BPI, they definitely want us to consider this. And we're going to have to either measure how much electricity the fridge uses to see if it's going to be cost effective. But that's our first priority, to see how much energy it uses. We're going to do that by using a watt meter to measure the electricity. And if the fridge is a high user and replacement has a SIR of 1 or greater, then that's definitely allowable. We may not be able to do like a super fancy one with all the bells and whistles, but we get them one that's the same size and energy efficient. Sometimes we might not be able to get to the outlet to test the fridge because we'll have to unplug it, plug it into our watt meter. If the fridge we just can't get to, it's built into a cabinet, the floor is built up around it, then there is an allowance to look up its usage if we can't measure it. For exam purposes, the only database they have for the exam is AHAM, which is American Home Appliance Manufacturers. I know a lot of people like to use Kubella better, and that's fine. But for the exam, they're not going to be mentioning that database, only the AHAM, American Home Appliance Manufacturers. And that these databases will have their energy usage when the fridge was new and then degraded over time, so that we can have a reasonable idea of how much it uses without being able to meter it. But if we can meter it, then we'll need to. And with the watt meter, we need to run the test at least 2 hours without any defrost cycle. We can run it longer, that's fine, but we don't want to do less than 2 hours, so we have a reasonable idea of how often it cycles. And we want to preferably disable the defrost so we can ensure that it's not going to kick on during our test. Alternatively, if it did kick on, then you'd have to do the test again without it. So they want to stress that we should try and disable it if we can. And the defrost cycle on these older fridges come in a couple different varieties of their controls. They're going to be in the fridge, and they're essentially timers. They're going to control when it cycles. So on here, see where it's circled in red where the little pin is, and that's going to rotate. And we can turn that to advance the cycle, and we can kick it into defrost and then out of defrost, so we know we're starting at the beginning of the cycle and we're not going to go into defrost during our 2 hours. So these are a couple different styles. They're going to be found in a variety of locations depending on the brand. They might be up by the light or in the back, or some of them on the bottom, and older ones on the back. Now, if you can't figure out the defrost cycle, then you just want to watch your test after the 2 hours and look at the peak wattage. If it went into defrost, then the peak wattage is going to be several hundred watts, while the average use or the normal use is going to be maybe 100 watts, probably less. And if it does kick into defrost, you're going to have to do the test again. So here's just kind of explanation how to cycle this into defrost. Now, the more expensive your watt meter is, the more math it's going to do for you. Some of them have memory. You can put in different utility rates. The minimum requirement for a watt meter is to measure kilowatt hours. And it can't really be a watt meter if it can't do that. So even if we have the most inexpensive watt meter, $20, Home Depot, we can still calculate our fridge usage. We're going to plug it in, hopefully disable the defrost, and let it run for at least 2 hours. After the end of our test, we're going to get from the watt meter the kilowatt usage that was during the time of the test. And then we need to know how long we ran the test for. Was it exactly 2 hours? Was it 3 hours, 4 hours? And we're going to convert that to minutes. And we'll just take our kilowatts hours measured divided by the minutes that we ran the test for. So if it was 2 hours, 120. Then once we know how much kilowatt hours it uses per minute, then it's basically just figuring out how many minutes are in a year. So 60 minutes an hour, 8,760 hours in a year. And then we've got the total usage for the whole year. If we got a nicer watt meter, it's going to do this math for us. And it'll just spit out kilowatt hours for the year. And if we want to know how much money that represents, then we just multiply by how much a kilowatt hour costs. Usually in the ballpark of about 10 cents, depending who the utility is. So if we can't move the fridge to get to the outlet, to plug it in, to measure it, then we can use the AHAM database to look it up. But only if we can't. Testing is the first priority. And we could test other appliances in the same way by plugging them into the watt meter. The fridge is going to be one of the biggest users and has the highest priority for sure. If we're having the fridge replaced, we need to include in that price all of the costs to replace it and then dispose and recycle of the old fridge. The client cannot keep the old fridge. And when we do our audit, we're going to collect the model and the serial number. So we make sure that they don't try to swap it out with another fridge. That way we can take that inefficient fridge, get it off the grid where no one is stuck with that inefficient unit. So we get it recycled according to all the appropriate EPA laws on refrigeration, the refrigerant in the refrigerator. And the contractor has to prove that they did recycle it. We have to have all that documentation. So switching gear from fridges to water heaters. Most people are going to have a standard tanked system, but regardless what kind of water heater they have, we're going to assess its condition, identify what kind of fuel it is, probably electric, maybe gas. And our first priority, if it's functioning, is to ensure it's set at the right temperature. That's the easy savings. Usually that's going to be 120 degrees, though sometimes you might want it warmer, but the default is 120. And we want to check that temperature at the nearest faucet to the water heater. And that's for health and safety, making sure the water heater isn't putting out so much heat that it's going to be a burn hazard. At 120 degrees, it's going to take over 5 minutes for that water to burn. Whereas if you're at 140, I think it's like a minute. You get 160 is like 5 seconds before it causes third-degree burn. So very high. The higher the temperature, the higher the burn risk. Now, another low cost, no cost measure, just like adjusting the water temperature, is insulating the first roughly 6 feet of water pipes coming off of the water heater, whether in the conditioned space or not. Then we definitely want to insulate all the water pipes outside the conditioned space, but even inside, this is deemed to be worthwhile because there's going to be some convective and conductive heat loss through those first several feet of pipe, both hot and cold. So that is worthwhile. If the unit's in bad shape, we're gonna see if it's cost effective or if we have the funding available to replace it. And then we're just looking at ways to reduce their hot water usage after we've assessed the appliance itself. So we'll make sure it's in good shape, not leaking, not rusted, falling apart. Depending where it's at, it may need to have earthquake straps. If it's in one of the earthquake zones, like I want to say that east of the Oregon Cascades is in a higher earthquake zone than west, but it also can vary by city and county code. If it's in the garage, it's going to have to be up off the ground. If it's combustion, just in case there's any sort of gas fumes or any sort of fumes in the garage, that's not going to ignite them. Pressure relief valves, most important for health and safety. It's the only thing that prevents the water heater from being a big bomb in the middle of the house. If the water heater overheats or overpressurizes, it could definitely explode or shoot out the roof. But the pressure relief valve is going to prevent that from happening. So if something happened, it shorted, and it was overheating, that pressure is going to be coming out of that. And it needs to be piped somewhere safe where it's not going to be a burn hazard, shoot off at somebody, or also damage the building. So sometimes it has to go to a pan, and the pan has to be piped out. So we're going to check the temperature at the closest faucet and try and get it dialed into about 120. If it's electric, it's going to have 2 elements. So we might need to adjust both of those to get it to 120. But a gas is going to have 1 thermostat. And the savings can be pretty good just turning down the water temperature. This is just going from 140 to 120. Average person or average household is going to save about $40 if they're using electricity to heat their water. But if they're a high user or the temperature's up higher, that can be over $100 a year. And all we did was go twist the knob on the water heater. Easy savings. Now, insulating the tank is not too common anymore, adding extra insulation to the tank. It was more common in the past when older water heaters had little or no insulation. But new water heaters from, not exactly sure what year, but in the 90s on, they're all super insulated, and most manufacturers prohibit insulation being installed over the tank because it's already super insulated. But if it is an older one, or it's more exposed in a severe climate, like in a garage in Alaska or something, then it could be worthwhile to add more insulation, but only if the manufacturer allows for it. Otherwise, in Oregon, not usually going to be worth it, and probably the manufacturer doesn't want that anyways. But if you have the need to install tank insulation, the method is going to be a little bit different if it's gas or electric, because if it's gas, we've got combustion occurring and we don't want the insulation near that combustion process. If the unit is in bad shape, or we find it to be a high user and we want to get a more efficient unit in there, most people have regular tanked water heaters, and that technology in them, whether it's electric or gas, has been the same pretty much since they hit the market. You know, a water heater today is pretty much the same thing as it was 50 years ago, just with more insulation. But they do have new technologies on the market, and you probably have seen most of these either in people's houses or showrooms. But we've got, for electric, we've got heat pump water heaters, and that can save a ton of energy. They're going to use half or even less than an electric water heater. But they are big, and some of them do cool the room that they're in. So you have to have a location to put a heat pump water heater that's big enough, and you don't mind it being air conditioned, essentially. So garage can be a good place for them. And they definitely do save a lot of energy. But there's also tankless water heaters. I'd stay away from electric tankless because they're not very efficient, but gas, since gas is so much cheaper than electricity, they can be worthwhile. And tankless water heaters are, the way that they save energy is they don't have standby loss. Having a big tank of hot water sitting around all the time, just waiting to be used, is going to cool off, and it's going to have to kick on, reheat, even though nobody even necessarily used any hot water, because the heat's being lost through the tank. A tankless or on demand doesn't have that problem. There is no tank, so there's no standby losses. But if you're a high user, you got a big household, you're using lots of hot water, that water isn't sitting in that tank for very long anyways. So you don't have a lot of standby loss. So from an energy savings perspective, a tankless is not good, not that great for a home that uses a lot of hot water, because it's not going to save them any energy, because the water's not staying in the tank very long. Now, there is the side benefit of, basically endless hot water, but that could end up biting you if you end up using more hot water now that you have endless supply. So tankless is best for people who don't use a lot of hot water, because if they had a tanked water heater, it'd be sitting around all the time, no one's using it, cools off, and has to heat back up, and nobody's even used any hot water. So small family, vacation houses, tankless, definitely gonna help save them. Then there's also solar water heaters, and these do tend to be pretty pricey. Last time I put one in, there was about $8,000 compared to a tankless at a couple grand, and kind of the same thing for a heat pump. It's quite a bit more, but can be cost effective depending on the location and what they were using to heat their water with before. Like if they had just a regular electric tanked water heater, this can be cost effective, but is a big initial investment of $8,000 or probably more. But if they're spending a substantial amount, then it can be worth it. If we do replace the water heater, we want to make sure the replacement is sized properly. And the way to size a water heater is not solely on the tank capacity. It's by the first hour rating is how you size a water heater. And you want to select a water heater that meets the needs of the home. So the first hour rating is basically how many gallons of hot water can it put out. And if our need is, we're going to have to figure out our need to make sure we can meet it. So to calculate that first hour rating, we're just going to essentially take the busiest hour of the day out of any given week, you know, whether it's Monday or Wednesday. Usually in the morning, everyone's getting ready for work or school, bathing, cooking, cleaning, shaving, doing the dishes, washing clothes. Have the customer figure out their busiest hour and start to calculate all these tasks, how much water, hot water is associated with it. Add it up, and that's your need for that first hour rating. And you want to find a water heater that meets or exceeds that. So if we figured our busiest hour of the day, we're using 50, 60 gallons of hot water. Well, if we get the 67 one, we're going to be pushing it, but should be able to keep up. So 67 on our first hour rating, that means it can put out 67 gallons of hot water. Does that mean the tank is 67 gallons? No, but the tank is going to be full of hot water, and as we use it, it's going to be able to recover some of that. So it'll be higher than the actual capacity. And different types of water heaters will have a different first hour rating. Gas is going to heat up far quicker than electric, and electric's going to heat up quicker than a heat pump. A heat pump water heater can take several hours, if not most of the day, to heat back up all that water. And that's why heat pump water heaters will have a much larger capacity. So they'll be usually 60 to 80 gallons to be comparable to a 40 or 50 gallon conventional tanked water heater, because it's going to have a slower recovery. So that's how you would calculate the first hour. And that's what you need to be looking at when sizing a replacement water heater. That way we don't put in a new one that doesn't meet their needs. And water heaters should be lasting at least 10 years. So we want to also think about what might happen in this household in the next 10 years. Are their parents gonna retire and live with them? Are the kids gonna graduate and move out? They have shifting needs. maybe this one will work now, but you know, later on it might be not enough. Once we've evaluated the hot water tank or system, then it's all about cutting down the hot water usage. Now, most activities don't require hot water. From washing the clothes and dishes, you can get soaps and detergents that work just fine in cold. Unless you have a need for sanitizing, then you would want to do hot, I guess. But normal loads is going to be fine with cold. If they want to use hot water at the tap, low flow faucet aerators and fixtures can help cut down on that hot water usage. And then of course that's going to cut down on water usage too. And most people have to pay for water. Low flow shower heads, and then taking showers over baths also is going to save more. And the faucet aerators, I think they're only going to test you on the QCI exam, but just in case, the replacements need to meet the federal limits on faucet aerators, which are pretty lax or not very conservative. I believe it's 2.5 gallons per minute on the shower and 1.5 on the faucets. And that's the federal limit. We can go lower, but if we're replacing them, then we can't go higher than those. And here we're looking at just, what about hot water leaks? Those are going to add up too. So getting those fixed can save a lot of money. And this is just on the water heat side, let alone the water side of things. They're going to have to pay for all this water. So on average, about $15 a year per leak. And this is a pretty small leak, 2 drips a minute. You can barely even notice that. You have to stare at it for a whole minute just to see the 2 drips. Versus a bad leak at a drip a second, just steady drip of hot water. That's going to be over $300 a year per leak. And then we got the price of water on top of it. So thankfully I thought ahead, I guess, and put the federal limits. So here they are, 2.5 gallons on the shower, and it was actually 2.2 on the faucets. Now I'm sure you guys are doing probably 1.5, or even lower, and that's fine. These are the maximum federal limits. Lower the better though. And the way that faucet aerators or shower aerators work is that they're adding air to the water, and some are better than others for sure. But by adding air to the water, it seems like the same volume of water, even though it's been sometimes significantly reduced. It's not like those old style ones where it's like a mist coming out and you can't even use it. These are adding the air to it to maintain the same amount of volume, so you can get the same amount, seemingly the same amount of water, while still reaping the savings from using less. And then just venting out the clothes dryer, or fixing that vent, going from hard duct to smooth, making it short as possible, has energy savings related to it. Because the cleaner, the smoother, the shorter the clothes dryer vent is, the more quickly we can dry the clothes. And clothes dryer is big energy user, especially if it's electric. So average 25 bucks, higher, the more they use the dryer, the higher their savings are going to be. So a high user, maybe $50. And these are based off of your average 11 cents kilowatt hour price. Now, renewable energy is not usually something we can do, but BPI wants us to consider it whenever possible or cost effective. So they have a little thing about that, whether it's photovoltaics, solar panels that are making electricity, or solar water heater, or even solar space heater, to wind or geothermal. But these kind of measures are usually reserved for when we have special grants specifically for them, which recently have been few and far between compared to a couple years ago. So we covered what baseload was or is. It's everything but their seasonal usage. It's not majorly affected by the weather. We looked at how much of their utility bill is associated with that, and also how to calculate that from their utility bills. We looked at some regular measures for reducing the base load, and there's new technology coming out all the time to help us save on base load, from smarter appliances to just plugging these appliances into smart switches, smart strips that can automatically turn off appliances when they're not being used. And another big issue with base load is the phantom vampire load, where appliances are seemingly off but still using a lot of energy, and sometimes just as much energy when they're off as when they're on. Cable boxes is one of the bigger culprits there. Even when it's off, it uses the same amount of energy when it's on. Computers and video games are better, but when they're in standby mode, so anything that's remote control is using energy when it's off and plugged in. But other devices that don't have a standby mode, don't have a remote control, like let's say the toaster, when assuming it's not a smart toaster, but a regular old-fashioned toaster, isn't using electricity when it's off. But if it had a screen, it had a remote or schedule, I don't know why you'd want any of those features in a toaster, but if it did, then it would be using energy when it's so-called off. Like a microwave isn't too bad, just a little clock going usually. But other devices like cable boxes and home entertainment, video games, can use a lot when they're off. And therefore, that's easy savings by getting them on smart switches that can automatically turn them off, all the way off. Though there's sometimes compatibility, like if you have a cable or satellite box and you turn that off, some brands got to go and reprogram. So you might not want to wait for that every time. But other things might save a ton of energy. Anyway, so wrapping this up, if we're going to replace the appliance, we want to make sure it's going to be cost effective and we're getting the most efficient unit, looking for Energy Star or better units. And another thing to be aware of, especially when we're doing our modeling software, is that as we reduce base load, the byproduct of base load where the energy is being wasted, that's mainly going to heat. So as we reduce base load, our heat load of our home is going to increase. Now in the summer, that's a good thing to make the house cooler, but in the winter, that means the furnace is going to have to make up that difference. Thankfully, the furnace is going to be far better at heating the house, far more efficient than the light bulbs and the TV and all the other base load. But just something to be aware of. So if you guys have any questions, be sure and voice those now, drop them in the chat box. I'm going to pull up the quiz for this section. All right, let's get that on your screen. And we've got 5 questions. So let's work on these questions, then also take a break. And let's say get back at it, give you guys about 20 minutes, take a break, work on these. So we'll call it 3:35 and we'll go over the questions. And if you guys think of any questions during that time, be sure to bring them up when you come back from the break. But until then, I'm gonna go ahead and hit the mute button and we'll get back at it at 3:35, go over these questions. All right, guys, 3:35. Let's do a quick sound off, make sure everyone's back. So either in the chat or unmute, just let me know that you're there. Thanks, Commander.
I'm here.
Thanks, Matt, Drew. Are you there, Noah?
Yep, I'm here.
Cool, thanks.
Yep.
Laura, are you there? Laura, are you back from break? Laura, if you can hear me, let me know. Either unmute or drop it in the chat box. Well, I guess can't wait for too long. So why don't we get going on these questions? Starting with number one, baseline is defined as, who wants to volunteer?
Dan, is this for number one?
Yeah, what do you get for number one?
I got a C, a home energy usage except the heating and cooling.
You got it, C. Perfect. Number two, what happens as base load electrical consumption is reduced?
Heat load is increased. Answer A.
Hey, there you go. Everybody's getting that one. Good work. So three, while analyzing a client's utility bills, electric baseload is calculated by. And Drew got it first with D.
Hey, Dan, on number two, I got a question on number two. So I was going to put none of the above. So can you explain A as heating load is increased?
Right, because as we reduce base load, so we have less base load usage, we have less of the waste, and the waste from base load is heat, and that heat's going into the house. So now we remove that heat from the base load by using less, and the furnace is going to have to make up the difference because the house isn't being sort of preheated by all the light bulbs and all the
Oh, okay. Okay, I understand. So the heating load that was coming from your CFLs or whatever, your incandescent lights and all that, those aren't being used as much because we switched to LEDs, so it lowered it, and now we're going to obviously have to make up for that heat loss.
Right.
Additionally getting before. Okay, great. Thank you.
Yeah, you bet. That's a great question. And that's a great thing in the summer when we're trying to keep things cool, but a little bit, the furnace is going to have to work a little bit harder in the winter, but that's not a big deal. The furnace is made to heat the house, and it's going to do so a lot more efficiently than some light bulbs. 4, Which of the following will reduce baseload consumption? Circle all that apply.
A and C. A and C.
Yeah, A and C, get some light bulbs in there. If we get, C is a little bit iffy, but if we get a more efficient unit than what was in there before, absolutely. So let's move on to 5. If you can't measure a refrigerator's electrical consumption, what should you do? We're just gonna have to Google it right on the AHAM. So we'll look it up in the database. On BPI, they're only gonna have the AHAM database, but in the field, a lot of people are using the Coupa Cabela. They seem to find that easier to navigate. So any questions about base load? All right, well, if you guys think of any, let me know. So next, let's move on to blower door. And I know most of you are doing blower doors already, so I'm gonna keep it short, but make sure you're ready for the exam. So let's get this lesson plan up on your screen. So at the end of the section, we're gonna have 5 questions. Got a few of the key terms here. Some good reference information. If you have never done a blower door, then I would check out Weatherization TV. They've got a couple series here, and they have the links also in these supplemental for blower door basics. And they spend about an hour going just in full detail on that blower door. But I know most of you are doing blower door already, so I won't dwell on that more than we need to, but make sure that you got some of these finer points for when it comes time for the exam. So let's get the presentation up on your screen. Should be seeing blower door basics. Alrighty, so this is blower door basics. We're gonna be covering, come on, there we go. We're gonna be covering the units of pressure and flow and how those relate to our diagnostic tests, such as blower door, and some of the finer details in setting up the blower door, making sure the house is ready for the test so we can get an accurate test and a reproducible test. We'll be looking at different ways that we can find air leakage using the blower door, and you'll learn some conversion factors about how to use the blower door number to find quickly the square inches. That way we can help the crew find the leaks. So we're going to be focusing mainly on the Minneapolis blower door. Most of everything is applicable to Retrotech 2, except for the manometer setup's going to be a hair different. But our blower door, the one in the picture is a older blower door 3 from Minneapolis, all set up, ready to go to see how airtight our house is. We're going to be using that to depressurize the home, as natural pressures are too small and too variable to reliably reproduce the test. So we're going to exaggerate the natural leakage with the blower door by 50 pascals, create this pressure difference between inside and outside, and then we can measure how quickly the air is coming back in, and therefore we'll be able to calculate how much leakage there is in the building. And we can use this to benchmark before and after, have the give the crews the idea of how much air infiltration they're looking for, the size of the holes. And then we can combine the blower door with other techniques to more thoroughly evaluate how well connected is the attic or the crawl space. So the manometer, it doesn't matter what kind of manometer it is, all of them measure one thing, and that's what makes them a manometer. A manometer measures pressure. Most of our manometers are dual channel, so it's 2-in-1. There are some single channels, but they're not very popular in weatherization. Though you might see them in HVAC. So our manometer, dual channel, measuring pressure. And when we measure pressure, we have to compare it to something else. So like let's say we're measuring our pressure in our car tire. We got the gauge and we're measuring PSI in the tire. And what the gauge is doing is comparing it to the atmospheric pressure. So when we're measuring pressure and we're trying to describe our setup, we're going to be using the term with reference to, and that's abbreviated as WRT. So we'll be measuring, say, the pressure in the house with reference to outside. But our unit of pressure is going to be the pascal. I'm sure you guys are very familiar with it at this point, but it's a really tiny, small unit of pressure. If we compare that to, say, PSI, a PSI is going to be, it's going to take like 7,000 pascals to make 1 PSI. And a PSI is not, I mean, it's a good amount of pressure, but it's not that much pressure. And we're putting 30 or more inside our car tires. So Pascal is super tiny, but the other unit of measurement that we'll be using from time to time is the inch of water column. And that's the amount of pressure it takes to raise water up a straw 1 inch. And that's equal to about 250 pascals. Water column, we need to be familiar with that, as a lot of HVAC contractors use that as their unit of choice. So when they're talking about the furnace, it's going to be in inches of water column. The manufacturer specs are going to be in inches of water column. But a lot of times we got to deal with way smaller units of pressure, 1, 2, 3 pascals. You couldn't even see that on an inch of water column. It'd be 0.0000. It'd be too tiny. So we need to be familiar with both how to convert. So if we had 0.1 inches of water column, 1/10, then that's basically 25 pascals. Or if we had 1/2 inch, that'd be 1/25. So we need to be familiar with how to convert. The real conversions like 249 and some fraction, but everyone is going to round it to 250. So our manometer can only measure pressure, but we're not really overly concerned about the pressure in the house for air tightness. We might be for other things, but not air tightness. We're more concerned about the flow, how much air is leaking out of the building. And we're going to be doing that, measuring that with the CFM, the cubic foot per minute. And a cubic foot's just a foot by a foot by a foot, roughly the size of a basketball. And if we write it as CFM or CFM with a N, letter N after it, then that is going to be for CFM natural, as opposed to CFM 50, which is with the blower door or duct blaster on, exaggerating the pressure. Or if it was CFM, say 25, then the pressure is exaggerated to 25. So I'm pretty sure everyone set up a blower door. You guys are familiar with the frame, the shroud, getting the fan in, and using all the rings. The two different brands are a little different, but they're not as different as you think. The little circles on the RetroTech are for super airtight houses that we're not going to be getting into. And then it has regular rings, just like the Minneapolis. Minneapolis does make smaller rings similar to RetroTech, but that's an add-on feature since most people don't need it. We're talking super airtight homes, less than a couple hundred CFM. But the rings are going to act as, it's kind of like gears in a car. Each ring can do a different range, and those ranges overlap a little bit, just like the gears in the car. The more airtight the house is, the more restricted the fan needs to be, hence the smaller rings and circles. The leakier it is, the more open, the more power we're going to need. We got the expanding frame, and we're going to get it all set up in the exterior door. Mainly, we're going to be talking about DG700. These principles are going to apply to other gauges too, but the actual buttons that you'll press might be a little bit different on your RetroTech, especially if you've got newer models like DM32 gauges. If you've got still have Magna Helic gauges around, those can be useful for a lot of things, but for the blower door is too cumbersome and not accurate enough. So definitely use a digital manometer only, at least for the blower door. So we're gonna need the house set up to do a blower door test. And normally with the blower door, we're depressurizing, sucking the air out of the house. So we'll need to ensure there's no fires going, can't have any fire, and any wood burning appliance needs to be fully buttoned up where the ashes don't pose a risk of coming out and getting sucked into our blower door, as that's going to make a really big mess and can ruin the carpet and the furniture. So don't take any chances with fireplaces or fires. If there's no doors, put some cardboard up and just tape it. Better to be safe than ruin the carpet. Other combustion appliances are going to need to be off. Water heater, if it's gas, or combustion on pilot lights so it doesn't kick on. We're going to close all the exterior windows, doors, and we're going to open the interior. Anything that moves air is off, like exhaust fans and clothes dryer. So once we got the house ready, we put up the blower door and the exterior door. And then we got to set up the manometer. And I got lots of tips in here, some step-by-step, how to set this up. I'm going to pull it up on my real manometer here in a sec to walk you through it a little bit better. But when our manometer is measuring, it only measures the pressure, but we want to find the flow. So when we connect our manometer to our blower door fan, and it measures the pressure over the fan or over these these ring coil here, it's taking an average pressure inside the fan, and it's going to use that plus the knowledge of what ring you installed to calculate the flow. So it only measures pressure and calculates everything else based on the information we give it. So here's the step-by-step. And I'm gonna pull it up on my manometer and get that on your screen. All right, you should be seeing my manometer now. And the way we're gonna set up the manometer is on the A channel. We're gonna be measuring the pressure in the house compared to outside. A lot of people remember this by green to grass, but the color of the hose doesn't really matter. But we get that on, and that's going outside through the shroud and at least 5 feet away from the fan. The top, if we have the manometer inside, that can just stay open. We don't need a hose there. B channel is always B to blower. Blower door, duct blaster, B to blower. So we're going to measure the pressure of the blower fan, and that's going to be on the input. Reference is going to be to the same spot that the front of the fan is, so inside the house. But if you ever run the blower door backwards, now you're gonna have to run it to the outside. But that's unusual setup. But for regular depressurized blower door, manometer in the house, then you can leave that open. So we get those two hoses hooked up. We turn the manometer on. Oh, sorry, bear with me, the batteries died in the manometer. Good timing. While I'm changing these batteries, quick tip on checking your battery level. When you turn on your manometer on the B channel, when it's first loading and that number blinks on there, that's your battery voltage. The lower it is, the lower your battery is. It should be about 9 volts if you got full battery. It's just a little tip there so you don't end up like me with a dead battery as soon as I go to use my manometer. Now these newer manometers have rechargeable batteries. Imagine that's pretty convenient. All right, get this manometer plugged back in. You think they'd have the software where it worked without the manometer? All right, you should be seeing the manometer on your screen. Fresh batteries. So we got our hoses hooked up. Notice it said 9.2. That's my voltage. Nice full batteries. And when you turn the DG700 on, it's going to default to pressure mode, meaning both the A and the B channel are measuring pressure. And these A and B channels are totally separated. They don't communicate side to side, only top to bottom. The mode we want for a blower door is we're going to use the A channel to change the pressure in the house, and we can monitor that with the A channel. And then with the B channel, we're going to measure the pressure of the fan, the blower door fan. And if we set the mode to pressure flow, then it's going to calculate the flow based on the pressure it's reading. So right now I press mode and it changed us to pressure flow. If I press mode again, it's going to take me to pressure flow at 50. And this mode is specifically for the blower door only. And what it does is it is going to calculate what the flow is at 50, even though we may not exactly be at 50. We might be plus or minus a bit. And it will convert it automatically. If we press it again, we get pressure flow at 25. This is for the duct blaster only, as most of the country, including BPI, tests the ducts at 25. We'll get to ducts, I think, on Tuesday. So for the blower door test, we want either pressure flow or pressure flow at 50 is also perfectly fine. And a lot of people just do that by default, so you don't have to be super precise on adjusting your fan pressure. So we turn it on, we press mode, and then we'll press device. But in this example here, our blower door is blower door number 3, the most common one, and it's first in the list. If we press it again, we can select other blower doors, blower door 4, or other devices like a duct blaster. But we'll leave it on blower door 3. And now we just want to make sure that the house is ready for the test. So all the exterior is closed, interior open, everything moves air off, furnace is off, combustion appliances are off. Then we want to make sure all the rings are on the blower door. We're going to start with them all on, and that means all of them. Not all of them, but the center one, but actually all of them. With all the rings totally buttoned up, then we can measure the baseline pressure. And the baseline pressure is just what the natural pressure is in the house at that given moment, which is it's gonna change, fluctuate all throughout the day and throughout the year. But we just want to know what it is at that moment in time so we can take an accurate reading. So to measure the baseline pressure, we're gonna press the baseline mode. Now the manometer is gonna say baseline, meaning it's ready to measure it. We're going to start the measurement by pressing the start button. And that's going to start recording the baseline for as long as we run it. And we're going to let it run until the baseline pressure stabilizes. Right now mine's reading 0 because I don't have an actual hose going outside. But if I did, it'd be fluctuating with the wind and the weather. So we wait for that to stabilize, might take 10 seconds, 30, might take a whole minute. Windier it is, the longer it's going to take. So this number, now that it's stabilized at 0, but if it was a number, say -1, that is our baseline pressure. So we can jot that down for reference just in case we lose it. and then we can hit enter. And when we hit enter, it's going to automatically adjust our 0 on our blower door to whatever our baseline was. So our manometer now shows 80J. That means adjusted for the baseline, and that it's ready to start the test. It should be roughly 0, but it's going to fluctuate too with the wind. So now that we have our baseline calibrated, now we're ready to take some of the rings off of our blower door. And it's kind of your best guess. Is it a smaller home, a tighter home, or is it a bigger, leakier home? And the tighter the house is, the more rings you want. The leakier, less rings. A lot of people just start with 1. So if you start with 1 ring on, you just want to tell the manometer you have 1 ring on by pressing the configuration button. Press it once, it went from open, now it says A1. A1, that's the ring that's on, not how many you removed, but how many are on. And you can change that on the fly if you need to adjust the rings. So now with the rings, some of the rings off, with the fan open, we're gonna turn the fan up on the rheostat, the little knob, crank it up gently, gradually till we get to 50. Making sure we're not creating any messes, pulling insulation, any soot or anything out of where we shouldn't be. If once we get to 50, if the screen is blinking low on the B channel, that means low pressure. We can increase the pressure by adding a ring. So we just add a ring and then press configuration again to match the number of rings installed. Then we'll have to crank it back up to 50 or pretty close to it. And then we can get our CFM reading. If we crank it all the way up and we can't hit 50, then we need to start taking rings off. And we should be able to get to 50 then with all the rings off. But let's say we couldn't, then the house is super ridiculously leaky. The blower door can measure leakage upwards of 5,000, though in my experience, usually maxes out about 4,000. So if you can't get a pressure, that means you're leakier than that. And to get any sort of reading, you're just going to have to take it to the highest pressure you can, say 30 pascals, 25 pascals. And you will need to turn off the pressure flow at 50 if you're too far away from 50, like you're halfway there, probably isn't going to be too accurate. But you could compare it. But there is a manual calculation also for doing can't reach 50. The manometer should handle it most of the time, but if you can't get very much pressure, there is a manual calculation. Usually it's printed right on the fan control, but definitely in the manometer instruction manual. So at like 25, if that was the highest pressure you could get, your first instinct is, okay, I just double it. No, that's not actually, it's not a linear formula like that. I don't remember exactly off the top of my head. I want to say it's 1.8, 1.6 that you would multiply it, but not a full 2. So check the manual if you can't reach 50, but that's going to be pretty rare that the house is that leaky. So let's jump back to the presentation. So here in this example, you can see we got the house to -50, full 50 pascals. Closer to 50, the better. But if you're at pressure flow at 50, it doesn't have to be super precise. 45 is going to be pretty accurate. And on the B channel, it's telling us our CFM flow. This case, 4257. That's a lot, depending how big our house is. And a quick way just to judge how airtight the house is, just compare the blower door to the square footage. If it's over the square footage, it's on the leakier side. If it's under, on the tighter. But we of course want to get it as tight as possible, regardless of how tight it is to begin with. So it gives us an idea where we're starting at. And with that number, we can quickly convert it into square inches, because 4,000 basketballs, or in this example, 5,000 basketballs a minute is pretty hard to visualize when you're trying to track down these leaks. I can't even imagine 5,000 basketballs inside of one house. So instead, you can convert it to square inches by simply dividing by 10 or dropping that last zero. So in this case, 5,000 becomes 500 square inches, which is about the size of that window this guy's coming through, 20 by 25. It's much easier to visualize. We got to send the crews to find this air leakage. It's easier for them to visualize how much they're after. Unfortunately, though, it's not all going to be in one spot. It's going to be all spread out with little leaks here and there. But together, it would all represent this amount. And they call this formula the approximate leakage area, the ALA. So this is a quick way, just quickly convert from CFM to square inches. It's not super accurate, but it's accurate enough to give us an idea. If we wanted to be perfectly accurate, you divide by 12, but by doing 10 gets you really close, and you don't need a calculator. Now, another unit to be familiar with is air changes per hour. Certain standards use air changes per hour. I believe ASHRAE 62.1 had a part in air changes per hour. So it can definitely come up. And air changes per hour is a nice unit, especially when you're comparing one building to another. Like if my house leaks 4,000 CFM, it's leaking like a sieve at 1,500 square feet. But if my 10,000 square foot warehouse has a CFM of 4,000, it's going to be pretty airtight. And what air changes per hour do is takes the volume of the building into account, so we can easily compare one building to another, regardless of its size, and see how they compare to each other. So to perform this calculation, we're going to do a blower door test, which is at CFM 50. So it's cubic feet per minute, but we want air changes per hour. So we got to go from minutes to hours. So we're going to multiply by 60 minutes an hour, and then we're going to divide by the volume of the building. And we've got our air change per hour. If we started with a CFM 50, we're going to end with a ACH 50. If we had CFM natural, we'll end with ACH natural. Older homes are going to be leakier than newer ones, but it kind of gives you an idea what sort of range to expect in a newer home, maybe 5 to 10. Older can be much higher. So we went through how to use the different calculations in conjunction with our manometer to calculate flow. Well, the manometer is doing that part, but we can calculate the approximate leakage area and figure out how big are the leaks. We can quantify it, so we can determine how much difference we made before and after. We can convert that into square inches so we can visualize it. And remember, we've got, for every inch of water column, 250 pascals. So we can convert between the two. So if you guys have any questions, be sure and voice those, drop them in the chat. I'm gonna get the quiz pulled up on your screen. All right, you should be seeing the blower door quiz up on your screen. There's 5 questions. So let's take about 10 minutes or so. We'll say 4:30 we'll go over this. Give you a minute to go through these, answer all these questions. All right, 4:30. Let's do a quick sound off, make sure everybody's back, and we can go over these questions. So just let me know that you're there. Thanks, Commander.
Made it back.
Thanks, Noah. Drew.
Matt's here.
Matt. Laura, thank you. So let's go through these questions. We got the first one, a manometer measures blank and calculates blank. Who wants to volunteer for this one? I didn't catch that, Matt, sorry.
C.
C is correct. Measures only pressure, but calculates flow. Good. 2, which of the following can be used with a blower door to find air leakage? Circle all that apply.
A, B, D.
A, B, and D. Right, pretty much all of it, but potpourri not going to really be the most accurate way to track air leakage. But we can feel it pretty good. We can use smoke, infrared. Number 3, while performing a blower door test, you measured the home to be 2250 CFM at 50. What is the approximate leakage area? And Laura's got it with B. Yeah, just drop that last 0. Pretty easy if you can remember the formula. So our 2,250 CFM becomes 225 square inches. Number 4, 1 inch of water column is equal to how many pascals? All right, Drew's got it with C, 250. So if we have half an inch of water column, 125, 0.1, 25, 0.2, 50. Last, number 5, what is the ACH 50 for the following building? All right, we got it. Got a couple here. A, 6.5. So remember, if we start with ACH 50, we're going to end, or we start with CFM 50, we're going to end with ACH 50. It's good work. You guys have any questions about anything we've covered so far?
Hey, Dan, can you just go over that last one, the math on that?
Yeah, good idea. Let's grab the marker here. So what we're going to do is we got to take our CFM 50, which is cubic feet per minute, and we need to turn that into hours. So we're just going to multiply by how many minutes are an hour, so 60. And we're going to divide that by the volume, which we'll do that separately. So let's do this first. Sorry, I can't figure out how to turn this eraser off. There we go. So first, we figure 1750 times 60. I'll have to write smaller. So you got 105,000. But we also need to know the volume to solve this. So we got to take the square footage, which is 2,000. Multiply by the volume or the height to get the volume. So we got 8-foot ceiling. So we get 16,000. So we start by, we got 1750 times 60 divided by the volume, which is 1600. So we take the 105,000 divided by 16,000. And we get 6.56 or 6.5 if we round it. So not too bad. We just got to remember that it's the volume that we need. Minutes to hours divided by the volume, and we got our ACH. Any other questions? Anything you guys want to follow up on? Let's see. Well, we're getting down. It's almost 5 on a Friday. Let's see. Take a look at this. All right, there we go. Close that drawing feature. Let's see. We were gonna do zonal pressure next, but I think we're just not gonna have quite enough time to finish it in one sitting. So why don't we go ahead and I don't want to hold you guys late on a Friday afternoon. So why don't we we'll call it early today, but on Monday we're gonna have to make it through the combustion. Let's pull up the schedule here. I did kind of front load everything, meaning as we progress, the schedule is going to get lighter just in case we need to make anything up. So yeah, on Monday, we're focusing mainly on combustion appliances, but we do need to get to the zonal pressure also on Monday. Infrared, we're going to table for the time being till later on in the week, as that's a pretty small part of the exam. Probably the smallest part of the exam is infrared. But probably the biggest part of the exam is going to be combustion appliances, which we're going to focus on Monday, as well as the zonal pressure. So keep working on your pre-exam if you haven't finished it already. And if you're feeling weak in any of the areas we've covered so far, be sure to bring any of your questions. But also there's tons of supplemental information in the lesson plan. For ASHRAE, there's also some extra exercises I threw in the exercise folder. And I usually have tons of more information on almost any of the subjects too. If you're curious, I've got more exercises if you need a little extra help on anything in particular. So that being said, after Monday, we'll just keep working through the schedule, and we should have ample time to get through everything, as it's going to get lighter and lighter by the end of the week. Friday, though, we'll plan on doing mainly review and then our own OTI exam, which is about 30, 35 questions. So it shouldn't take too long, maybe an hour or so to get through the whole exam. Then I'll make sure that you're ready for the field portion, which is just going to consist of you sending me the video of you doing the couple tasks, blower door and a couple things. So I'll make sure you have that list and that's all clear. And then once I get the video, will suffice for your field portion. And then on Friday, we'll do the written. Once you've completed both of those and you have your BPI approval letter, then you'll be eligible to sit the real BPI exam, which I know we can do the written remotely. Still working out the details on doing the field remotely, but we'll be in contact and getting that all set up once you're ready to take the BPI exam, which is a written 100 question exam, and then the field exam it's one of the longer exams, longer than our OTI one, but you get a maximum of 4 hours to complete that exam. We'll spend some time going over that. I've got some instructions written up too on just walking you through that field exam. We'll go through that, make sure you're ready, and then we'll be in contact and getting it scheduled. So does anybody have any questions about the schedule or any of the information we've covered? As always, if you guys think of any, be sure and bring them, send me an email. We'll make sure that all your questions are answered and you're prepared, ready to go. But no other questions at this point. We'll call it a day and we'll pick up on Monday, 1 o'clock, and keep our schedule rolling. And I guess that's about it. You guys have a good weekend. And take care, and I'll see you on Monday.
We can.
All right, bye, guys.